Try to solve another Leetcode problem 2571, minimum operations to reduce an integer to 0. We are given a positive integer n, and we just want to do the following operations any number of times, so we can add or subtract a power of 2. So we're going to return the minimum number of operations to make n equal to 0. So we need to understand what is the power of 2. So the power of 2, so for this 2 to the power of I, and I going to be more than or equal to 0. So this is the number x. It's going to be a power of 2. So for example, if n equals to 39, our first step is that we're going to plus 2 to the power of 0. So it's going to become 40. So this is the first step. After that, we're going to reduce 2 to the power of 3. It's going to become 32, and then we're going to reduce 2 to the power of 5. It's going to become 0. So how many steps? 1, 2, 3 steps. So we're going to return 3, and this is going to be the minimum number of steps. How can we solve this problem? Maybe the easiest way is by using dynamic programming. I mean the DFS plus memorization. So the idea is that, for example, we have a number. Let's say we have a number 9. What is the minimum number of steps to make this 9 to 0? And definitely it's going to be 2 steps. We can reduce a 1 and we can reduce this one. Yeah, so this is the idea because we have 2 1-bit, but this is not the minimum. So what about we have some numbers like this one? So this is 15. Yeah, it is actually not 4 steps. We don't need to reduce 1, reduce another 1-bit, and reduce another 1-bit, and reduce another 1-bit. Instead 4, it's going to be 2 steps. Yeah, because for this one, we can plus 1 instead of reduce a 1. So we can plus 1, so it's going to become something like 1 0 0 and 0, and then we just need to reduce this 1-bit, so it's going to become something 0. So it's going to be 2 steps instead of 4 steps. And similarly for this example, let's just try to explain the first example. So how can we do it? We're going to use the lowbit property. So for any binary number, we know that we can use 01 to get the lowbit. So the lowbit is going to be this number and another number. So this number with the negative this number. So we can get to the lowbit. So for example, this number is 9 and negative 9. It's going to become 1. So this one going to be the lowbit. Yeah, so we're gonna use plus a lowbit and minus a lowbit. So what if we plus a lowbit plus this one? So it's gonna become 1 0 1 0. Now we can minus this lowbit. It's gonna become 1 0 0 0. Now we're gonna continue to do the operations. We're gonna plus this lowbit and minus this lowbit. If we plus this lowbit, it's gonna become 1 1 0 0. If we reduce this lowbit, it's gonna become 1 0 0 0. As we know that if a number, this is our edge cases, if the number only has 1 lowbit, it is only this one lowbit, it just needs 1 operation. So from here we're gonna return a 1, and from here we're just gonna continue. It's gonna become, we're gonna plus 1, it's gonna become 1 0 0 0 and 0. From this side it's gonna minus 1, it's gonna become something like 1 0 0 0, and from this one we're gonna return a 1. And from this one, we're going to return a 1 because there's only 1 lowbit. And similarly, we're going to continue from here. So from here, we can plus 1. It's going to become something like 1 with 4 zeros. And from the right side, we're going to reduce a 1. It's going to become 0. So this means that there's only 1 step if we find only 1 lowbit. So in total, how many operations? It's going to be minimum of the 2 sides, minimum of the left and minimum of the right. So minimum, what is the minimum of the left side? So how many operations? 1. So this is did I do something wrong? No. So from the left side, this is 1 operation. This is 2 operation. It becomes 1000, and we still need another operation. So from the left side, the minimum is 3, and from the right side, the minimum is 2, because we can turn this to 1 0 0 0, and then we still need 1 step to make it 0. So you know, if we have some number like the binary number like 1 0 0 0, definitely there's 1 step, and we're gonna use another formula. I forget about the formula. The formula is x add x minus 1. Yeah. So if a number is 2, so 2 add 1, so 2 and 1, 0, 1, it's going to become 0. We need to, yeah, I think this formula is going to be easy to remember. So for any binary number, if this number is a power of 2, so this means this number and this number minus 1, it's going to become 0. So this is another property to check if a number is a power of 2. And this is a formula for lowbit. Yeah. I mean, normally we don't do such operations for binary numbers, but at least if we were to use the bit manipulation, we have to remember some kind of a formula. Yeah, actually it is not so difficult to remember if we are doing such problems. And for this one, definitely we're going to use DFS with memorization. As you can see, if we find something like 1000 or 13 zeros, here we also have 13 zeros, here we also have 13 zeros, it means a lot of the computer is repeating by itself. Yeah, it means we don't need to go all the branches, so this means we can use dynamic programming to solve the problem. Yeah. Now let's just use a case, and with a function, we're going to call it a DFS. So the edge case is that if x and let's say x minus 1 equal to 0, so this means this is the edge case. We can return a 1. We just need to one step to return this number. So if this number is 2 to the power of 3, we just need one step to make it a 0. And this is a yeah, obvious. Now we can divide this lowbit. Actually, we already know how to calculate this lowbit. It's going to be x with negative x. Finally, we just need to return our final result, as we already used one step. Yeah, because if we were to do one operation, we already used one step, and then we're gonna plus the minimum of the left side and the right side. So it's going to be x plus the lowbit, and DFS with x minus this lowbit according to the definition of the problem. Finally, we just need to return the DFS with this number n. Now let me just run it to check if it works. As you can see, it works. Now let me just submit it. As you can see, it passed for all testing cases, and it's pretty fast. And the time complexity is just O(n), and n is 10 to the power 5. Thanks for watching. See you next time.